back to Learning Physics with me. Today, we're going to be learning about drag force. Drag force is the opposite force of the main force propelling an object through space. A great example of drag force is the experiment that we're going to do today. We're going to hold coffee filters at a certain height above the ground, and we're going to drop them. So, what are the two forces acting on the coffee filters when we hold them at a certain height? The coffee filters are sitting up here above the ground at a certain height. Now, gravity is always pulling on these coffee filters, this direction, right? Now, this arrow represents the gravity acting on the coffee filters. It's always going to be the same magnitude because gravity will never ever change. But as we drop the coffee filter, this is T0. This is before we drop it. And then after we drop it, maybe here at T equals 1, what happens to gravity? Like we said, it remains the same. It's going to be the same magnitude. But now there's a little bit of that drag force that we were talking about acting this way. You see it's represented by a very small arrow because it just began to fall. So maybe here at T equals 2 seconds, it falls a little bit more. Gravity remains exactly the same, 9.8 meters per second. But here, the drag force gets a little bigger. And even still, further still, at T equals 3 seconds, coffee filter falls a little bit more. Gravity remains the same. I should draw this one a little bit less, but here, maybe at T equals 3 seconds, the drag force approaches the same, almost exactly the same amount of force as gravity does. Now, what happens when these two almost equal? So, what does happen when they almost equal? Here is T equals 0, time versus velocity, T equals 0. We first dropped the coffee filters. What happened? It was speeding up because gravity was pulling on the coffee filter so hard. Now, what do you think is going to happen to the velocity as it gets further on in time? Remember, maybe at T1, the drag force was acting a little bit. So, okay, it starts to slow down. The velocity starts to slow down a little bit. Remember at time when it was 2 seconds, the drag force is acting even more on it, so it slows down even more. Now the slope is less, and then at T equal 3 seconds, it pretty much flatlined. That's because the drag force was equaling the gravitational force. So at that point in our representation, it was 3 seconds. At 3 seconds, it reached this what we call terminal velocity, and that's when the gravitational force and the drag force are just about equal, and in our case, the coffee filters will no longer gain any more velocity. Now, I'm going to go outside and actually drop some filters, and we're going to put it on the tracker software, and we're going to see if the graph that we theoretically came up with is actually going to match the real world. And then once we get that graph, we're going to model it in the code and see if that graph matches the real world data. So here it is. You can see we're standing at the top and we drop the coffee filters and tracker tracks the filters as they fall through space. Now keep an eye on the graph to the right. You see how it starts off on an acceleration and then it gradually evens out where it no longer gains velocity. Now that we have real-world data from our experiment, we can find what's called the drag constant. Now the drag constant is very important that we find because we're going to plug it into the code and it's going to update the force that's acting on the object that we're going to program. To find it, all we have to do is set the force weight equal to the force of the drag. Now we know that we weighed the coffee filters before the experiment and it was 0.101 kilograms. We multiply that by the gravitational constant, and this number here, 3 meters per second, was the terminal velocity from the experiment. It took it it took the coffee filters about 2 seconds to reach 3 meters per second, and then at that point, they were no longer gaining any more velocity. So if we multiply this out, we get about 0.32 Newton meter seconds.
Now here we have the code. At the top up here, we have just where the graphs will be created, just the visuals of the graphs that you'll see down here on the bottom right. Here are the constants like the mass, the gravitational constant, the drag coefficient, which we calculated earlier, and the initial velocity, which was 0, time, which was 0, and the delta t that the code is going to be using to update is at 0.01 seconds. So it's going to be very accurate. The while loop down here is what we're always concerned about every week. This is how the code's going to be updating over time. So we're defining what the weight is. Remember from that formula that I just showed you, the weight, the drag, and the force is what's different this week. The force is being updated with the weight plus the drag. And that's going to change the velocity because the velocity is updating by adding the force dividing by the mass times that delta t, of course. So that's what's different this week. And we can also get the potential energy, kinetic energy, and total energy right here. And it's going to be graphed out down here. But we're always concerned about the energy in physics. So that's something else that we can test. So let's run the code and see what happens. See, the box is simulating the coffee filters as it was dropped from that height of about 5 meters. These are the graphs from the position, velocity, and the energy graphs. And we're going to compare these to the real life graphs that we got. Here are the graphs that we took from the real world experiment. Here is potential energy, kinetic energy, and finally total energy, which is just kinetic and potential added together. And here is the graph made by the code.
So let's find out how good we did. We're going to find the percent difference of our experimental data versus the modeling data. The video actually took 2.2 seconds to finish, where the coffee filters reach from the top to the floor. Now in the computer model, it took 2 seconds. Now we're going to subtract those two numbers, divide by the average, and multiply by 100 to get a percent difference. That actually comes out to be 9.5%. That is a very good percent difference. Anything under 10% we can work with.
So you can go back and analyze those graphs a little more. You go back and pause the video if you want to, but you'll see that they all matched up very, very well. And that's why we got such a great percent difference on the time, because everything in the video matched up with everything in the real world. So now you know a little bit more about drag force. Thank you for watching.